What would it take to connect a 40-year-old Commodore Pet to the internet and play a YouTube video? What would be required to play, say, a 30 FPS video streaming from YouTube in full rate and with no dropped frames? This is the story of one such attempt. Since the Pet doesn't have any network connectivity, we need to hook it up to some type of device. There are only a few ports available. The cassette port is designed for serial communication. It's quite slow. The IEEE port is much more capable. It contains an 8-bit parallel bus and several control lines. Unfortunately, it's already being used by this SD card adapter. So we are left with a user port. We can ignore the upper part. It contains video output and diagnostic signals. The lower part has an 8-bit wide I/O bus and two control lines, CA1, which is the input, and CB2, which will be used as an output. The next question is, what kind of device should we attach? I've been wanting to use this Raspberry Pi Zero for a while now, and I think its tiny size will keep things small. Its built-in Wi-Fi will make the Pet go wireless. Obviously, we need to build some kind of adapter between the Pet and the Pi. This green cloud adapter must be fast enough to transfer the video stream. To know how fast, we'll need to look at the receiving end, that is, the display of the Pet. The Pet screen is 80 characters wide and 25 characters high. That gives us 2000 characters per screen, where each character is described by 1 byte. Since we want to display 30 frames per second, we get 60 kilobytes per second to display on screen. Let's look at the Pet architecture as taken from the October 1983 service manual to see what it takes for the Pet to transfer 60,000 characters per second to the screen. Here is the user port. Here is the IC that interfaces the user port. Here is the video controller, and over here we have the RAM. Some of the RAM is the video memory, the 2000 bytes. Finally, to the far left we have the CPU. Note what is absent from this diagram. There is no direct memory access controller. This means that if some data is to be transferred from one memory location to another, it is the CPU that has to do this. So when the characters are to be updated on screen, it is the CPU that has to copy them there. We have at most 16.7 microseconds to spend per byte, and probably less because we need to do some other stuff than just copy bytes to the screen. However, since the Pet is clocked at 1 MHz, this translates to just 16 clock cycles, or even less. So how much work can the Pet do in 16 clock cycles? Let's have a look at the instruction set. Here we have an add instruction, add memory to accumulator with carry. There are different variants depending on how you access the memory, the addressing mode. Depending on which one, the instruction takes between 2 and 6 cycles to finish. If you scroll down, you will see similar values for the other instructions as well. On average, an instruction takes 4 cycles or so. This means that the 16 cycles translates into roughly 4 instructions per displayed character. That leaves no time at all to do any video decoding or running a TCP/IP stack. It seems like there is not even time to communicate with the Pi. I kind of doubt the viability of this with this tight compute budget. Anyway, let's see what we can make the Raspberry Pi do. We need to stream the video from YouTube, and YouTube DL is a program that we can use for that. YouTube DL has some issues, both legal and technical lately, so I instead chose to use YTDLP. It's pretty easy to use. Just clone the repository and then invoke the shell script yt-dlp.sh. In this case, I'm listing which formats a particular video is available in. I'm interested in format 135 because it has a size that doesn't require rescaling, because that is an expensive operation. I can crop it to the size I want without losing too much information. Then it is a simple matter to retrieve the file. That is all you need to do to grab a file from YouTube. Alright, now we have sorted the video streaming to the Pi. We now need to decode it. OpenCV can decode many video formats and deliver individual frames in an easy-to-use format. OpenCV stands for Open Computer Vision and has pre-compiled packages for many platforms. Raspberry Pi Zero does not seem to be one of them, however, but one can easily build it manually. Just follow the build instructions. Here it is put together as a large script. Then execute the script and OpenCV will be cloned from the repository and built. It took the poor Raspberry Pi Zero 15 hours to finish. Things went ahead just fine until everything suddenly came to a full stop. OpenCV complained that the Pi Zero didn't have the necessary hardware support, in particular that the processor lacked the Neon instruction set. Neon is an extension to the ARM instruction set that enables simultaneous operation on multiple data elements, like here, where 4 integers are added independently of each other in a single instruction. It is typically used by applications to accelerate signal processing or render graphics. This was so bad news that I had to verify by 2 other sources, and sure enough, both Linux and the web agreed that the Pi Zero indeed lacked Neon support. This is a showstopper for the Raspberry Pi Zero, since there is no chance to succeed without Neon. Fortunately, there is now a Pi Zero 2 out, and we can see that it actually has a Cortex A53 processor. What does ARM say about that? Well, it does indeed have support for Neon, so it's a simple matter of ordering a Pi Zero 2. But when I do, the component shortage comes in the way. This DigiKey experience is representative for all major suppliers, out of stock and no known lead time. I guess I'll just have to wait and hope that I can get hold of one somehow. In the meantime, I will continue on the pet side. So, given this architecture, what can we do with 4 instructions? For instance, how much time would it take to first read the user output and then store it into the video memory? To assess that, I've built a model of the system in Kretsim. Kretsim is a digital circuit simulator that I wrote to help with the circuit design. To the left we have a model of the Pet, and to the right we have the model of the Pi, and in the middle we have the circuitry that we will talk about in a bit. Let's look into the Pet model. It's a rather simple model with 1 CPU, some RAM and the U-support IC, which manages the U-support signals. If we take a closer look at the SRAM by checking out its parameters, we can see that it contains a file. This is a program file that was generated by compiling an assembly file. And let's have a quick look at it. There is a lot of stuff here, but the blue region contains the interesting stuff. It's this code that copies the data from the U-support to the screen memory. It just happens to be 4 instructions, and for each iteration in the loop, 1 character is copied. So how long does this take? Well, let's find out. So here is the result of a simulation for the transmission of 2000 bytes. Let's zoom in on a transmission cycle. Here we can see some interesting signals like the CPU address bus, the data bus, the read-write signal and the clock. I will not dive into the details, but this is the first time we write to the screen address. We can see that the read-write signal is going low. And if we move to the right, we can see where we fetch the next byte from the U-support here, and even further to the right we can see the write signal goes low again, indicating that we make another write to the screen memory. So this is the time it takes to copy 1 character. So we can count the number of clock cycles. 1, 2, 13, 14. This means that the Pet cannot do much else than just copy whatever comes on the U-support directly to screen memory. It also means that the link must transfer already prepared screens ready to be shown by the Pet, and that the Pi has to do all the heavy lifting. It is also at this point that any hope of sound goes out the window. Alright, since there is no Raspberry Pi 02 in sight, we'll have to do with the old Raspberry Pi 2, which has similar performance. We know that OpenCV gives us a sequence of nice, colorful images, and we also know that the Raspberry Pi must convert these into ready-to-use character screens that the Pet can display. First, separate the transfer from the conversion. Then we need to think about the conversion from the nice image to the rough character representation. I have made a separate video on how to do that. See the link in the description. Basically, there are 3 steps. The first is removal of the color information. The second is an approximation in which the grayscales are replaced with a black and white dot pattern. And the last is mapping the dot pattern onto the Pet character set. The first step is trivial, so I'll skip that. In the second step, I use a method called Floyd-Steinberg dithering, in which one approximates the gray level with a black or white pixel. The error that one makes in that approximation is propagated to the neighboring cells, so the error is smeared out over the image, creating a nice looking bit pattern. For this video I added a small twist. I spread out the error not only in the current frame, but I also forward some of the error to the next frame. By doing so, I allow pixels to turn on and off quickly. This switching pixels add to the grayscale illusion, especially if the monitor has a long decay time. At least this is the theory. The final step is to approximate the bit pattern with the characters from the Commodore Pet font. I've chosen the upper font for this experiment. The way I choose which character that best fits the bit pattern is to do an XOR between the two and count the number of set bits, which is the number of positions in which the two are different. Then I select the character with the lowest number of differing pixels. This has to be done for all the characters on screen, and since we have 2000 of them, and need to test against 256 characters for each, we have to make 500,000 tests per screen. Needless to say, this test needs to go pretty quickly. This is the function for computing the difference between the bit pattern and the character. The data type is an unsigned 32-bit integer, since we started out on a Raspberry Pi 0, which is a 32-bit architecture. Here we do the XOR operation, and here we count the number of set bits. We need to do it all over again to cover all 64 pixels. XOR and the number of set bits. This means that we do just over 1 million count bit operations per frame. This operation is also known as a Hamming weight or pop count, and there are many different implementations, like this C code here, or assembly language, or even a function that is built into the compiler. Okay, so that's basically how the Raspberry Pi should convert the images to the character display. Now, the $1 million question is, can it be made fast enough? I have written an implementation and a benchmark to measure how quick it is. This benchmark is running on a Raspberry Pi 2, which should be as fast as a Raspberry Pi 2 0. Drift.mp4 is a pre-downloaded video that is used for all the benchmarks. Here we can see the timings for the different processing steps. Let's put them into a nice table. The dithering and approximation steps are by far the heaviest, with 75 and 114 milliseconds respectively. The total sum is a whopping 220 milliseconds, and that is not good, because if these results stand, we could only show the video with 4.5 frames per second. However, we have not switched on the optimizations yet, so let's see what happens if we switch on the highest level optimization, -03. That was odd. Looks like we're in for some hardcore optimizations. Since we are so constrained by the compute cycles on the Pet, just 14 of them and 4 instructions per character, there is no room for any handshaking between the Pi and the Pet on a pixel basis. So the handshaking will need to be done one screenful at a time. This means that we need to buffer an entire screen between the Pi and the Pet, and therefore need to store the screen in a memory between the two. This is a dual-port 2K SRAM. Dual port means that it has 2 address buses, one for right and one for left, as well as 2 data buses for right and left. It also has duplicated control signals. The right-hand side is connected to the Pi, while the left is connected to the Pet. Another reason for this memory is that the Pi will have to transfer the screen to memory as fast as it can to free up some time for video decoding and approximation. That will take 2 milliseconds or so. The Pet will also read it as fast as it can, but even at full speed it will take close to 30 milliseconds. Now, there is a problem connecting this RAM to the user port. As we saw before, we can only use 10 bits of the user port for signals. However, the memory interface requires no less than 23 for its use. The biggest problem is that we can't generate an address to the memory. We only have one output that isn't data, and that is the CB2. We can solve this by adding an address generator that consists of a counter and a timer. When we activate CB2, the timer starts and the counter issues us address 0, address 1, 2, 3, 4 and so on. A free running counter means that the Pet must be quick on its feet and read whatever comes out of the memory exactly at the same pace as the counter generates the addresses. Too early or too late and the Pet will read the wrong data. This is perhaps a corny illustration, but the assembly program read operation must align up with the address generator for all the characters in memory. So read access number 2000 cannot differ more than ±7 cycles. With a modern computer such as the Pi, this would be impossible since the execution time jitters much more than this. However, the old and trusted Pet executes at a very constant speed because the architecture is dead simple, so we just need to adjust the speed to match. The problem is that the required accuracy of the assembly loop is 0.0035 cycles. That is a problem when adding or removing an assembly instruction adds or removes a couple of whole cycles to the loop timing. We'll talk about how to pull that off in a minute, but first we need to address the video decoding problem. Last time we got these surprising and disappointing results. Something isn't right here. These two columns are way too similar. I know for a fact that I switched on the optimizations, but maybe let's double check the make file. -03 should give us the highest level optimization, but maybe if I shout at the compiler really loud it will do as I want. Let's try to run the benchmark again. There we have it. Let's put it into the table. Now we are getting somewhere. We're down to 41.6 milliseconds or 24 FPS for the entire chain. We could of course optimize some more, or we could use the fact that we have several cores in the processor. Set that we place the frame decode, conversion and dithering on one core. That would then take 22 milliseconds, and place the approximation and transfer on the other core, and that would take 19 milliseconds. Obviously, they cannot run in parallel. First we need to do the decode and conversion, and then after that the approximation. But they can work in parallel by using pipelining. Let's give core number 1 the first frame to work with, and when that is finished, hand it over to core number 2. While core number 2 works on that frame, core number 1 starts processing the next frame, and then repeat that for the coming frames. In this way, the pace will be set by the longest of the two, that is 22 milliseconds. So we could run this at a rate of almost 45 frames per second. I'm not too fond of multi-core programming. It is a little bit of a hassle. Maybe I'll try to optimize the pop count function with assembly language or rewrite it to a 64-bit implementation instead. I guess time will tell. In any case, we need to address the hardware timing issue. The idea now is to build the circuitry between the PET and the Pi and then test it by sending one or more dummy screens through it. When that is working reliably and fast enough, we could think about sending real content. So here we are back again in Kretsim, and this is the circuitry between the PET and the Pi. At the center we have the dual port memory. We find the ports for the left side here and the right side here, and to the far right we have the model of the Raspberry Pi. This part is new. It is the address generator for the Pi. It takes in a reset signal and a clock signal from the Pi. If we look inside, it contains 3 4-bit counters that together form a 12-bit counter that is the address for the memory. And that is attached to the right-hand side of the memory. The data bus is directly connected between the Pi and the memory. This makes this address generator different from that on the PET side. Here we can step the address whenever we want by manually generating pulses on the clock pin. So we do not need to race against some external clock, which is good, because the Pi jitter would be way too high for that. On the left-hand side we have the PET model that we looked into earlier, with CB2 acting as the start signal to the address generator for the PET side. Let's have a quick look at it. Here we see the same construct as for the Pi address generator, 3 4-bit counters forming a 12-bit address. This is the clock generator that sets the pace for the readout for the assembly program to match. This clock is connected to the counters above. Finally, this circuit reacts to the CB2 start signal by setting the address to 0 and start counting. It automatically stops when it wraps around. Alright, so this is the circuit that we need to build. Basically, it's simple. 1 memory and 2 address generators, one of which is manually clocked and the other races against time. Here I've hooked it up all on a breadboard. We have the Raspberry Pi 0 over here, and this is the clock signal and some other stuff going to the 3 4-bit counters in the Pi address generator. This is the generated address, and the data bus connects directly from the Pi to the memory. So this is the dual port memory. On the left hand side we have the PET user port, and its signals are brought onto the breadboard here. The start signal goes into the PET address generator at this point. So these are the 3 counters that generate the address for the other side of the memory. The data bus for this side of the memory is of course connected to the PETs. That's it. Let us see how this works. The first step was just to read stuff from the user port and display it on screen, which was quick and easy, but there is no content to be shown yet. The next step was to generate the dummy screen. That required that I solved the timing issue. I knew the inner assembly loop would take close to or very close to 14 cycles. Therefore I made sure that the timer ran at exactly 1 MHz, same as the PET, and then divided it by 14, so it should match the assembly program quite closely, although not exactly. When I ran it, after some troubleshooting of course, it first looked quite alright, but then I realized that I had to tweak it somewhat. Here is where I start the timer, pulling CB2 low, and here is an initial delay to hit the first byte correctly. I actually skip memory position 0, since that carries back keyboard information to the Pi. Then we have the inner loops of the copying, but between these loops I had to insert an extra instruction because I was running ever so slightly fast. This adds 1 extra instruction per 256 iterations of the loop, or 2 cycles for every 3600, so on average I slowed down by 0.056%. Luckily this adjustment was just enough to match the hardware clock. When this and a couple of other issues were fixed, I managed to have a rather smooth scroll. It looks a little bit better in person because the update frequency of the copying, the CRT refresh rate and the camera capture rate interfered to make it look a little bit jerkier than it actually is. Guess what showed up in the mail today? A Raspberry Pi 20W. I finally got hold of one. It took a lot of searching and I had to pay an arm and a leg to get it. Let's see how fast it is. I think these numbers are faster. Let's compare them to the others. And what do you know? These numbers shrank across the board. Well, not the OpenCV stuff, but the rest. The frame conversion was cut in half, the dithering shrank by a quarter, and so did the approximation. As far as this benchmark is concerned, the Raspberry Pi Zero 2 is much faster than the old Raspberry Pi 2. But the fantastic news for us is that the total sum is 33 milliseconds, which makes it possible to run this just above 30 frames per second, which was our goal. So no neon or assembly optimization and no multi-core implementation. And of course I replaced the Pi Zero on the breadboard at once. We are now capable and ready to run a larger portion of the chain, from a downloaded clip, through the image conversion, through the electronics and its memory, and finally rendering it on the PET. So, time for the first big test. First we need to start the Pi program, called Bixterm, and when that's ready we can start up the PET program. The program we see loaded here is an improved version of the assembly program, but it still doesn't do anything more than just copy the data from the user port to the screen and feed back keystrokes to the Pi. I've added some menus and stuff to the Pi program since we last saw it. Drift is the video that I used for the benchmark, and it doesn't actually connect to YouTube, just read from a local file. Up to the left we can see that I've added an FPS counter, and it shows almost 30 FPS as predicted. I still have some tweaking to do in the approximation and the dithering code, but basically it works as anticipated. So, since everything works as expected, it's time to tidy things up a bit. The first step is to make a proper PCB of the breadboard design. I use KiCad for the PCB design. Here we have the PET connector. In the middle we have the memory. And in this box we can see the 3 counters of the PET address generator. We generate the exact clock in this circuit. And over here we have the Pi address generator, also containing 3 counters. To the far right we have the Pi connector. I used the paper and marker method to verify that the schematics correspond to the breadboard design. When I was satisfied that everything was okay, I did the layout. I placed the Pi connector at the bottom and the PET connector at the top. The finished board should look something like this. The last step is to upload the design to the PCB manufacturing site. This site offers a preview of the uploaded files, and it's usually a good idea to look things over. When done, add to cart and proceed to checkout. While waiting for the PCB to arrive, I took the time to design a little box. It consists of 2 halves, with text engraved on the top and some holes for the LEDs. There are M3 screw holes coming up from the bottom, and there are cutouts for the PCB, the power connector and the on-off switch. Then I put my 3D printer to work. The result was pretty horrible, and the engraved text didn't turn out at all as I hoped. Instead of fixing the 3D printer issue, I was lazy and brushed some XTC 3D epoxy on it to cover up all the problems. Since the recessed letters on the top didn't work out as expected, I printed a new set of characters. I sanded them to remove some rough edges and then covered them with the same epoxy stuff. It created a pretty glossy surface that I could put some paint on. It worked out pretty nice. The last step was to glue them to the box. The top and bottom snap together like this, and the box is finished. After 2.5 weeks of waiting, the PCB finally arrived, so it is time to solder all the components to the board. Since the user port doesn't provide any 5-volt power, we need to have an external power supply. In the end I will have a proper 5-volt adapter, but this will do for now. I chose a rocket switch for on-off. Of course I made a couple of mistakes, for instance the placement of the LEDs and a signal being connected to the wrong pin, but the by far biggest mistake was the orientation of the Pi connector, as you can see in this test run. It should have been rotated 180 degrees so the Pi would hover above the board, not extending outside it. Fixing these mistakes and producing a new board took me 3 weeks, but by the magic of filmmaking it was done in the blink of an eye. With the new version of the board, it's time to put everything together. So, there it is. Time to play with it. We're back where we started, but now let's go for option number 2 instead. While I was waiting for the PCBs to arrive, I took the opportunity to implement a terminal emulator as well, now that I could transfer screens quickly to the Pet. This is a full Z shell terminal, and even my fancy prompt is rendered correctly. It's very quick, actually just as quick as the Raspberry Pi itself is. I have mapped the control key to the RVS key down to the left, so I can actually run even Emacs. The terminal emulation is almost working good enough to support all the antics of Emacs, but there are still some quirks to work out. This is the assembly program that you've seen before, and right now it is showing the code that actually runs on this machine. You may recognize the CB2 activation here, and the timing knobs, and the time critical copying loop. It is also possible to browse some simple websites using links. But the terminal is not why we are here. Let's look at some YouTube videos. Unlike last time, we are now actually using the YouTube DLP script to stream the video from YouTube into the decoder. Not every video works, it has to be big moving things for the illusion to work. Let's try another. Let's try a third video and comment on some effects. Let's pause for a moment. Do you remember the temporal Floyd-Steinberg dithering where I sent some of the error into the next frame? If one were not to have that, the selected character would only depend on a single frame and not the history. Well, let's see what it looks like with and without that. Above the line we have the temporal method, and below it the ordinary one. And it makes no difference at all. There you have it. Enjoy the rocket science.
Would be a corruption of a God-given ability.
10, 9, ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running.